critical mass of people, and we started the recording. So, hi everyone. Today on our agenda we have a work of Dr. McCarthy. Marika has graduated. She got her BA in physics from Willamette University, actually where SPD was in 2017. And then she was in grad school at Montana State University working with Dana Longcope on coronal loops. And she defended her dissertation earlier this month. And this is her dissertation talk, which I thought was awesome. So I invited her to give it to everyone. And congratulations, Marika, again. And let's start.
Awesome. Yeah, thank you for the invitation and for the introduction. I am just realizing now that my slides have my defense date, but we will just ignore that for the moment. So yes, I've been looking at coronal loops, specifically between adjacent quiescent active regions. As far as an outline, I'm going to be talking about, the 3 chapters of my dissertation. The introduction I'll probably gloss over a bit here because my dissertation talk included a wider audience, including like my parents and my grandma. And then I'll end with conclusions and some exposition about the future. So we all know that the sun has an atmosphere, which, most people might not know that, or most astrophysicists might just think of the atmosphere as the surface. But in order to view the atmosphere of the sun, you have to be in the right place at the right time, like in the path of totality for a total solar eclipse. Or if that right place is space, that time can be all the time, for instance, with atmospheric imaging assembly on SDO. Yes. So this is just a little bit about active regions and coronal loops that I will kind of gloss over for this talk. Yes, and so the whole idea is that within the solar interior, the pressure keeps these long flux tubes keeps them partitioned, keeps them from interacting with each other within the interior. And so then these distinct magnetic systems can only kind of begin to interact in the corona post-emergence. And so it's this kind of laboratory in which I have examined magnetic reconnection, fundamentally changing the topologies of these magnetic field lines. And so here's hope you can see my pointer. Here's this little cartoon. We have our 2 adjacent active regions coming into contact in the corona. And then now they've reconnected to these new domains where I've indicated the different magnetic domains in this quadrupolar model by the different colors. And so over the course of 24 hours, looking at the emergence of active region 11149, so you'll see it kind of emerge down here adjacent to this larger 11147 up here on the top. We can kind of see how this topological change happens. So we have, new flux emerging to the south here. We see, indications in the field in EUV. And then, after about 48 hours, this region has, emerged, and we actually see evidence of these interconnecting loops between the 2. So now I'll kind of detail the investigation. Oh, uh-oh, what happened here? What did I do? Okay, sorry about this. Trying to avoid all this complication. Ah!
No worries.
All right, hopefully we're back up and running. Ah, oh my gosh, what am I doing? Are you able to see this?
Yes.
Okay, perfect. Sorry about that. So yeah, now we'll kind of detail the, oh yes. And so yeah, so here's kind of the evidence of the reconnected flux. We see the evidence of coronal loops between the 2, and that would kind of correspond to maybe this kind of green domain here at the bottom. Okay, first, what might we expect to see? We first built a model where each active region is reduced to a positive and negative kind of magnetic charge informed by the strength of each polarity from the magnetogram data. And then the whole system of the 2 active regions is a quadrupole. You can kind of see that here. Maybe it's not showing up that great, but we have a kind of a positive polarity here, a negative polarity here, and then a positive negative kind of down here in the emerging active region. And then this orange line on this plot, oh, sorry, I should say, and in this plot, we have this existing active region. So this system here is the solid black line. The emerging active region is kind of the dashed line here. And then the orange line in this plot is the flux we expect to see connect the 2 active regions in a vacuum in the form of the loops shown in red here on this bottom panel. But then we can make our comparisons with reality by actually cataloging these interconnecting loops. And so we build a time-space stack plot by taking this strip of pixels between the 2 active regions from a series of successive 171 angstrom AIA images, and then stacking them on top of each other in order to get this time-space stack plot. And we choose the slit such that every loop that connects between these 2 regions will cross the slit. And then because loops are bright, they cause local maxima along the slit and appear in the stack plot as bright streaks in time. And then we ID the local maxima along each slit and then link them in time. And then part of our process involves a manual confirmation step, which is seen in this panel. So all these peaks are kind of identified along the slit, but then maybe this feature out here doesn't look to be very loop-like, and so we would exclude that from our catalog. And then the verified loops are shown here on this stack plot in red, and from this cataloging procedure, we also get information about loop diameter and loop lifetime. And for now, I'll just note this delay between emergence and the onset of the bulk of reconnection, 13 hours, kind of, there's not a lot of red going on in this section of the stack plot. And that's kind of similar to other reported results in the literature. Yeah, so we choose to analyze the interconnecting loops and the flux budget transferred into this interconnecting domain using what we have called this AlphaH modeling technique by Annie, where the ingredients are you take a traced loop in an EUV image and you compare that to a series of linear force-free fields whose boundary information is taken from the boundary information is taken from a magnetogram. And so you use your trace loop and kind of match it to the best linear force-free field to which it fits. And after that, you have a full 3-dimensional model, an individualized 3D model for every loop fit in this process. And you can kind of see an example here where we have 4 different loops that have been fit with this technique. And this is from the same set of loops, just viewed from different angles. So a little more different and then a little more different. We've also used these fields in these fits, in other ways, including to construct a full 3-dimensional non-linear force-free field. So now it's time to revisit the interconnecting flux, this time as informed by the data. And it's common to assume that a loop has a circular cross-section and our loops intersect our slit approximately perpendicularly, so we don't consider the projection effects of that cross-section. So then using the diameter from the cataloging procedure and the individual magnetic field strength for that particular loop at the location where the loop intersects the slit, we can obtain the loop's individual flux. And then after accumulating them all, we have interconnected flux over time. And then I will mention for loops we may have missed during the modeling procedure, we use a median value informed by the modeling results. Yeah, and that's seen here in this kind of red line. What's of concern, however, is that our results suggest that there's more interconnecting flux in this domain than is even available to be given up from the emerging active region. And this was our big takeaway of this work, which was published in 2019 in AppJ. How can this region have more flux than in the AR? And so what could have gone astray? So we know flux is the integral of B dot dA. Perhaps something's faulty with B, so there's inaccuracies in our modeling method. Or something went wrong with areas. Maybe the cross-sectional areas are not circular as commonly assumed. And cross-section circularity has been a commonplace assumption for decades, with Jim Klimchuk in 2000 is as being cited as early evidence for circularity. And then loops are hypothesized to expand as they rise into the atmosphere to preserve their flux along their length. And what if that expansion is not isotropic in all directions, but anisotropic as proposed by Malinishenko and Shriver? And that whole idea may be that loops might look different based on how they are observed. For instance, in this cartoon, you might look through the emitting material in this way, where you're seeing a large diameter, but you're not looking through a lot of emitting material. So a loop might look wide. You might infer that a loop looks wide and kind of dim, versus if you look at it from 90 degrees different, then you're looking through more emitting material, but you see a narrower diameter. So the loop might look narrow, excuse me, narrow and bright. Yes, and so this idea of loops not having circular cross sections has been tested since, with results that seem to continue to support loop circularity. Or a final explanation for our takeaway might be that we are seeing loops brighten multiple times. For instance, in this work, we assume that every time a loop became bright, it was the first time this flux had reconnected. And it was only newly reconnecting flux that was populating this interconnecting region. So yes, this is what we, in the 2019 paper, attributed our overcounting of flux to. And specifically, we said that flux might again rebrighten as it releases energy to reach a lower energy state or another process that's kind of internal to this interconnecting region. Yes, and we proposed Taylor relaxation. So this figure looks at where, so basically, okay, this figure looks at where the loops intersect the plane of the slit. So basically, if we were to take the slit, we're looking at it edge on in the stack plot kind of figures. If you were to look at it face on, these are the locations where the loops from our AlphaH modeling would intersect that plane. And in this figure, there's kind of an overlap percentage of about 70%. And when we account for this, were we to scale the overcounted interconnecting flux that was in red on the previous plot by 30%, the remaining 30%, the non-overlap percentage, the amount of interconnecting flux is brought more in line with the predictions of the quadrupolar model. Yes, and in the more sophisticated model that we used in Longcope et al. 2020, that includes domains that are internal to this interconnecting region, loops appear to be formed at topological boundaries, which kind of suggests the internal relaxing or reconnecting that I mentioned. So we were first motivated to look at loops as a vehicle by which we could investigate reconnection. And then the takeaway from this 2019 paper is kind of like the impetus that we had to investigate these loops in other ways. And the first 2 points we will investigate through a stereoscopic study, and then the latter will investigate by looking at this event in multiple temperatures. And this stereoscopic study was recently published in AppJ, and I think some people might have saw me give a talk on this specific section at SPD a couple months ago. Yes, and so when I used this example when I was explaining this to my mom of thinking of a stereoscopy as like a 3D movie where you have two-dimensional images from slightly different angles and it gives you three-dimensionality. And we already have three-dimensional models from the AlphaH fitting procedure itself using one perspective. However, we will use the aptly named stereo mission to provide us a new perspective. In fact, it'll provide us two different perspectives using EUVI data, again, in 171 angstroms. For this event, AIA is giving this Earth perspective here, and then we're really lucky that the A and B instruments are almost in quadrature with that. So again, referring down to this kind of cartoon here, it's really nice if we want to see or potentially see any differences in anisotropic loop expansion. As far as the data set goes, we have 56 instances of AlphaH fitting, and we have 199 tracks created from those AIA images. And when I say a track, I specifically mean the three-dimensional model that results from the AlphaH fitting. And I will refer to a loop as the underlying EUV feature. So up here in this panel, the tracks are kind of these colored lines, the models laid on top of the image, and I will say that the loops themselves are the underlying EUV features. Yeah. And so our approach here is different than conventional stereo usage. For instance, in traditional stereoscopy, you kind of make your inference in triangulation. You begin with points in space from one perspective that lie along some line of sight from the second perspective. And for this example, we might have, and then you look along these lines of sight and try to identify which features might be of interest. And for this specific example, maybe the 3 points better fit this blue shape or this yellow shape. This point line of sight doesn't really intersect this pink triangle. But potentially from this angle, because the pink triangle is the brightest feature, maybe that's what we identify, even though there might be features that would be better candidates from our triangulation. So we choose not to make our inference there, but we do our inference when we create our tracks. So in this way, we can look at what we know in the second perspective, and we'll look to kind of confirm our fits instead of construct them. And so the way that we test our AlphaH fitting veracity is by looking at them. We rotate our tracks into this second perspective and assign them to one of three categories: an excellent match, a maybe match, or a no match. Here are some examples. So we would call this green and orange track, we would call those both excellent matches to kind of this feature underneath it, kind of despite the ambiguity between them. And then I believe we call this cyan a no match because it doesn't seem to have any features underneath it in the EUV image. Yes, I believe we called the orange and green here maybe matches. If you squint, you might be able to see the features that I thought they corresponded to, although we do have supplemental figures available in AppJ if you want to go through and kind of do this assignment yourself. There's an asterisk, a star on this cyan image. We chose to exclude things like this from consideration, though we could call it a maybe match because it maybe lies within the saturation. We just chose to exclude it from consideration instead. And I will say, I think I forgot to mention this earlier, but this event kind of was rotating across disk center from the AIA viewing angle. And so from the A and B angles, it kind of rotates either from the far side of the disk to the near side or vice versa, depending on which stereo you're using. And so, for instance, we would exclude this cyan track from consideration because this actually lies on the far side of the disk. And so we don't want to muddy our statistics with things that we know that we cannot see. And here are the category assignments for all of the tracks we considered. you know, there's a pretty good split. There's almost 70% of tracks that we could identify with some underlying feature, and then 30% that we could not. So now we've tested the fitting veracity, the truthfulness of that. Now to look at kind of the second prong of our investigation, where we want to do this method of diameter comparison. And we did this more rigorous investigation for 13 track loop pairs that we thought were suitable for this quantitative diameter analysis. So a track is composed of a set of points in space, and for each point in space, we consider that the point of interest, for instance, the star here. So for each point of interest, we draw concentric circles around the point of interest, and along the perimeter of each circle, we look for the local maxima, which maxima in intensity, which should trace out kind of the spine of the loop. And between the, on either side, between the local maxima, we look for local minima, which would be kind of like the edges or the perpendicular direction to the loop. Then we take the edges, the intensity of these edges, and plot them here and fit it with a Gaussian. And we extract the parameters Gaussian peak A, which we use as a proxy for intensity, centroid B, which is the loop location or the deviation from the point of interest. And then we use the full width at half max as our diameter. And we also do this for the corresponding AIA image. And so in this way, we can compare the same point along a track from 2 or even 3 different perspectives. Our method is new, but for well-fit tracks, so kind of on this side of the dividing line, so the well-fit tracks, it's very comparable to the method of straightening a loop. So here's our track, and then this red box corresponds to this red here, and then the really well agreement is an orange and is kind of right here. Yes, but we chose to kind of, it fits well with this established method, but for our set of data, we chose to use our method because it's not guaranteed that our AlphaH fitting method will result in tracks that match reality exactly. So we're not guaranteed to have the, for instance, over here, we're not guaranteed to have the direction perpendicular to the track be perpendicular to the loop. We could choose to, you know, go in and trace these by hand, but not only is that more work for me, but we've already decided where we're making our inference. I'll reference again this cartoon, but we really want to let the kind of tracks guide our analysis and not kind of involve more inference than we've already decided that we would make. Or basically, we've already decided we want to make our inference step when we create our tracks. We don't want to introduce any more inference if we're to go through and trace these by hand again. I think that's all I wanted to say. So here's a key example. My favorite key example is this purple track, which is well fit to the underlying structure. All the plots are in purple because we're looking at the purple track. Yes, so here's our intensity and diameter information. We get kind of negative correlated behavior. Down here we have AIA diameter versus EUVI diameter, and that's kind of correlated. And down here we have diameter information along the track, and then the centroid location or deviation from the point of deviation from the track along the track over here, kind of in black. And then I will note that we have, for all of these fits, we denoted what we called regions of good fit, and that's this region between the vertical dotted lines. Yes. So here's my results slide. It is a laundry list, which on their own are all well and good, but I want to point out takeaways in pink that kind of speak to the evidence of non-circular loops. In terms of fitting agreement, or in terms of fitting agreement, it's pretty decent. We have 70% agreement, but then there's the whole issue of this third of the data that might be missing. But is it really missing? Or maybe it's just not seen from this perspective. It's not quite analogous, but if you think about a piece of paper, and if you were to look at that piece of paper edge on, you might not be able to see it from that angle, even though it exists and you're able to see it quite well from other viewing angles. So for these loops specifically, maybe there is just such anisotropic expansion that there's not enough emitting material along the column from this line of sight for it to be seen. Yes, in terms of diameter comparisons, we observed an anti-correlation in 8 out of 13 track loop pairs. An elongated object might look larger from one viewpoint than the other when observations are in quadrature. Persistent correlated behavior might be more in line with the traditional idea of a circular loop that's expanding. Or a circular cross-section expanded loop. Yeah. And then as far as a diameter versus intensity comparison, for the EUVI viewing angle, we observed an anti-correlation between full width at half max and intensity for 6 out of 13 track loop pairs. And the perspective given by AIA does not exhibit the same behavior consistently. And so this might speak to changing diameters from one perspective and not the other. So, maybe these things are changing anisotropically themselves. The big result is that 4 of our 13 loops exhibit both anti-correlation, so for diameter, and for diameter versus intensity. And we cite this as evidence of ellipticality, and this is kind of in contrast to the recent results of Terry Kucera and Klimchuk and DeForest, or Terry Kucera et al., excuse me. And so this kind of supports the emerging idea of cross-section deformation, major minor axes, anisotropies, and yeah, it's been really interesting to hear feedback on these results since their publication. So that was great, an interesting result, but now we'll kind of return to this idea about loops brightening multiple times, or observations of loop cooling. Yes. So maybe the most famous example is Ashwandin and Alexander in their analysis of the Bastille Day event, seeing cooling loops cooling loops from 30 to 1 megakelvin, where they used an aggregate light curve over the field of view, assuming that a superposition of loops would behave like a single loop. And there's been extensive work by Weil and Klimchuk using AIA with its many channels, both in small sections and also in pixel by pixel analysis of data cubes. In contrast to this, for this section, we seek to use whole loop structures rather than relying on light curves. The catalog that was first composed in the 2019 work is expanded here to include loops from 193 and 211 angstroms using the same kind of cataloging method. We chose these channels because their responses to temperature are relatively uncomplicated and they form sort of a stepladder in temperature. In the table, you can kind of see some of the parameters extracted from the catalog, the number identified, their median diameter, and their median lifetimes. And I will note that kind of this color assignment, so gold for 171, kind of brown for 193, and this magenta for 211 kind of persists. These color assignments kind of persist throughout this section. I will point out there seems to be, in just looking at the number of loops identified in each channel, we have 211 containing the least, followed by 171, and 193 angstroms containing the most. And so this was the first kind of inkling that we got that maybe we might be seeing two different loop populations. We might be seeing loops that are heated to above 2 megakelvin and cool to temperatures that are above 0.6. And then we also might have this other population of loops that are heated to below 2 megakelvin and then are become cool enough to be seen in this 171 passband. So we have loops that might occupy these two and loops that might be seen in these two. So we want to observe these loops cooling through these different channels, but there's this idea, can we even expect to see them? So first off, this is an intensity versus location plot. So intensity in data number per second. Location is distance along the slit. This right histogram is, the locations where loops appear to be. And I will point out that the combination of the 171 and 211 loops kind of imitate the shape of, so the combination of these two channels is given in green. It kind of imitates the shape of this, of the 193 loops kind of underneath it in brown. Where is I going with this? Yes, okay. So now the intensity observed in passband P is a product of the emission measure and the response function of passband P, where RP max is the temperature of the band's peak response. Yes. And so now we want to see what the intensities in bandpass P might look like when viewed in P prime. And so intensity of passband P prime is related to the intensity in passband P in this way, involving this new parameter in this exponent. And we use two different values of nu to align the median intensity of the 193 data with either of the other two. These plots are interesting to read, but basically to read them, data read against the like colored axis is the real intensity value, and data read against the other colors is synthesized brightness. So basically, if we were to read this plot, if we were to read the gold data against the gold axis, that's the true intensities of the 171 band passes. But if we were to read the brown data against the gold axis, that's what the synthesized, what the 193 data would look like. It's synthetic data of what the 193 loops would look like when viewed in 171. All right. So no choice of nu would align all three observations. So in fact, either choice to align either 171 with 193 or 193 with 211 here takes the observation seemingly below the detection threshold of the third bandpass. So we align the brown and gold here together, and that kind of, takes the intensities to kind of below the detection, the general detectivity, I guess, of the 211 band pass, and vice versa here. So now both these band passes kind of are on the less bright end of this distribution here. And now we return to our stack plot, now this time with data from all three band passes. Yes, and so the first thing is, where do these loops appear concurrently, both in space and time? My inclination, and maybe you see the same thing too, but the brown and gold seem to occur together quite frequently. I also think that 193 and 211, so the brown and magenta, also appear at some points together. And the 171 and 211 data don't really appear together that frequently at all. There's also this time delay discrepancy. I previously mentioned a delay between emergence and reconnection, about 13 hours. And it seems that the 193 angstrom loops also exhibit the same time delay. But there's one significantly shorter when we're looking at the 211 data. And we can compare this to a collection of other delays reported in the literature using different event types. So 13 hours delay, a 13-hour delay that I mentioned is on the low end of typical, but 4 hours is very short. Longcope et al. 2005 was the first group to report on these delays, and they cited a possible threshold that must be reached before reconnection can take place. And they also posited that they weren't seeing a hot component, which was related to the undercounting of flux that happened in that study. But the shorter delay here observed in 211, and also in this work by Tar, who also used 211 angstroms to calculate reconnection rates. And this is 11, which is, still on the lower end, even though it's kind of a more typical sort of delay. But the shorter delays observed here and with Tar in the Tar work lend credence to the idea that hot loops might be first reconnected and then cooler loops might appear after a time threshold. Yeah, so this is a small sample size, but it's kind of an interesting seed of an idea that we would expect hot loops or things to happen in the hotter channels much earlier than in cooler channels. Yes, and so we also noticed some general morphological trends during cataloging. And so which domains that these loops seem to live in seems to coincide with the bandpass used to observe them. So these are 3 different images from each of our 3 bandpasses. I will note that the green box, these are taken at different times first, and the green box is only meant to show the area of interest, not necessarily to say anything. The deformation of the green box isn't really meant to say anything. But the 171 channel exhibits a lot of kind of these loops here, kind of centrally located. In 193, we see those same sorts of loops, but we also see these like longer lasting persistent features over here on the left. And these features are seen in 211, but 211 also has these long features that kind of arch over to kind of this polarity over here. And what's interesting is we don't seem to see signatures of these types of loops in 211. In fact, like these kind of loops seem to kind of arch over the location where these loops might be. So for these loops that are in 2 different populations, perhaps they are somehow partitioned in space as well as in temperature. Like in the 2019 work, we can examine the flux budget in this region, but unlike in the 2019 work, here we use a characteristic B value. So we have to be careful as this is fundamentally a cross-sectional area comparison across all 3 bandpasses. And though I did comment on it in the earlier section, we do assume that loops have circular cross-sections for this section. We can take a derivative to get the voltage data here on the right, and then the same data has been smoothed in 2 different ways between these 2 panels for visual clarity. For general trends, what first became apparent is again the similarities between 171 and 193, especially after 20 hours into the event. So they kind of trend the same. There's like a kind of a burst here, it levels off here, and then kind of rises together again. I also want to point out a specific instance of there being kind of an inverse response to voltage from one channel versus the others. So over here in cyan is, it's around the end of that 13 hours, so after the delay. So the voltages of the 171 and 193 passband kind of take a jump, while the 211 bandpass kind of reacts oppositely to that. And this might be further evidence of two populations, or this phased reconnection. We have all this activity happening in 211, and then that drops off, and then the activity begins to happen in 171 and 193. This is kind of in opposition to this here, this circled navy area, where the simultaneous response might be the more traditional picture of loop cooling. And we can make a comparison of brightnesses, both in space and time. So this, these three figures here are more expanded versions of our both our stack plot and kind of our intensities plot over here. And we kind of create these plots, we create these masks by considering the pixels bright that are within the loop's median radius from its identified location. And then the mask for the loop's first appearance is in color. And yeah, so this is basically a stack plot with diameter information in it as well. Summing in the time direction, we can get a brightness fraction. So the amount of time a pixel was considered bright, and that's shown in these bottom three panels in black. And we can also get a brightening rate. So how many loops brightened per hour at that location along the slit, and that's given in color. And then these don't look as similar, again, as we might expect for loops wholly moving across temperature bands. And so the question then becomes, like, why don't we see what other studies are seeing? You know, the cooling observed, you know, in the Bastille Day event or by the work of Weil and Klimchuk seem to exhibit this aggregated cooling behavior. And so loops are hypothesized to be multi-threaded, composed of strands at scales smaller than we can currently observe. And so, you know, we can see them kind of looking like pasta noodles, but perhaps they are more like embroidery thread in that way. We propose that this distance might be because these other methods are better insulated from or account more accurately than our method of these underlying structure. So by looking at light curves, perhaps, you know, you might be able to see the multi-threaded, or maybe see the multi-threaded behavior, account for it somehow better than what we're doing, where we're just looking at whole loop structures. Yes, and so the takeaways from this multi-wavelength study, we expect impulsive heating followed by observations of loop cooling. But the evidence that we've compiled here supports the idea of two populations of loops that are partitioned by temperature. Maybe they're delineated by an internal reconnection relaxation process. And by that, I mean, maybe, you know, one population of loops is those loops that are initially reconnected to populate this interconnecting domain. And the other population of loops are loops that, you know, now are able to relax and reconnect internally to this region. I did mention, or maybe I didn't mention this, but we didn't do the AlphaH fitting on the 193 or 211 angstrom loops. So perhaps more modeling would bring up more differences between these populations. And perhaps differences in our approach can aid in probing underlying substructures of loops. And so as far as conclusions go, in this work, we've challenged a variety of assumptions, so that loops only brighten when newly reconnected. We've challenged the assumption of loop cross-section circularity and challenged the traditional notion of whole loops cooling. And we've also kind of verified our AlphaH fitting method. And then as far as looking to the future, we have a rich catalog of loops from different passbands. You can do a lot with them. And a couple examples. It's an idea that I kind of toyed with earlier with just the set of loops from 171, where we're looking at their the evolution of their shape in time. So again, if you're looking through kind of this emitting material this way, this is what you might infer that you're seeing. But maybe in time, there's some sort of change in the loop's orientation, or the part of the loop that the part of the loop that's along your line of sight. And now the loop might change kind of from looking like this to maybe you infer something that looks like this, and you might expect, something like this. Plenty of other things to discover. 2 active region systems are a rich laboratory, and kind of this idea, was brought up by Jim at SPD, where it kind of relates to this idea where these 2 active regions are kind of approaching the same flux magnitude. And for constant alpha fields, the local and large scale fields are linked. So here's the aggregate alpha values of the interconnecting region and of the individual regions themselves. And so, the alpha values, the distribution here and here look, similar enough. And so maybe these 2 active regions that we had initially thought might not be, or these active regions that, we initially assume are 2 independent systems, maybe they're not as isolated as we once thought, which, was an idea that Dana and I had at the very beginning of this work. Yes, then in the future, more modeling, foot point evolution on loop heating, multi-instrument studies of active regions to come, beginning fall 2021. Great. And then here's my acknowledgement slide. I do want to point out, this is me right here. This was from the 2015 Montana State Solar Physics REU. So I'm a product of a successful REU program. I think that's I'm a good example of, I think, what the NSF wants from these summer programs. But with that, I'm ready to thank you for listening, and I'm ready to take any questions you might have.
Thank you for the talk, Marika. And we have quite a few, 1, 2, 3, 4, 5, 6 comments/questions in the chat. I will read them.
Okay.
So the first one is from Jim. It makes sense that loops would brighten multiple times, not just because the initial stress can be released in bursts, but because the loops get distressed by continuing foot point driving. So he kind of seems to...
Not de-stressed, not a re-stress. They're continually getting stressed by the driving.
Re-stressed, thank you. And then the next comment is, I presume you found the D that is for the fitting of the Gaussian profiles, the coefficients A, B, C, D. So I presume you found that D is considerably larger than A in your fits. The background is considerably brighter than the loop itself.
I don't recall. I don't think so. D is larger. I don't think D was significantly larger than A, but I would have to go back and look at that again.
Just a quick comment. In the loops I've studied, typically the loops themselves are only like 10, 20, 30% as bright as the background. Interesting.
Yeah, I will have to double check. I thought these loops were pretty bright, but again, I don't have a good recollection.
Let me also say, very nice talk, Marika. Really enjoyed it. Very clear.
Thank you.
So more comments. I will just keep reading them. Jim, feel free to join in and correct me, or anything there. So also, what is the aspect ratio of the ellipses? By my thinking, anything less than 2, 3 or so is circular.
Ooh, interesting. I don't think I calculated an exact aspect ratio. I should do that.
I just want to make the point that when I talk about circular cross sections, I don't really believe it's a true circle, and it can be, quite different from a circle.
Yeah.
The point I like to make is that the aspect ratio is not very large, whereas some physical modeling might suggest it could be very large.
Okay.
Okay.
Sorry, I just wanted to make a comment related to that. I was just trying to think of a good analogy for these loops, and I think a parachute, like the type that paragliders have, like the top of it looks it's very, top of it is very wide, but then suddenly if they change direction and you only see the edge, you wouldn't be able to see it. And this goes back to the piece of paper analogy.
Yeah.
But the loop, the loop, if the loop would look like that, then yeah, it would disappear. So the absence of the 30% absence in your detected loops, yeah, it could certainly be evidence for this kind of very extreme, aspect ratio. Thank you.
Yeah.
Okay, so this is also from Jim. In your position time plots, how do you explain loops that disappear in 211 but do not subsequently appear in 193 and 171? Do the loops get hotter than 211?
Yeah, that's interesting.
Before you addressed it, sorry.
Oh.
Yeah, you talked about this quite a bit.
Okay, one more from Gabe. A decrease in density in the loops could also reduce emission in all channels. Was there evidence of coronal rain forming in these loops?
We didn't look at these loops. Well, part of a detriment for the method that we use to look at these loops is that we use that virtual slit, and so we were it was a significant reduction in the data. Just in my own kind of observation of like this event, I don't have it, or like observations of coronal rain didn't really jump out at me, but I haven't again looked at it quite in depth.
Okay. Then there's a comment by Jim to what Gabi just said. I presume you would see sequential cooling and warming with thermal non-equilibrium, the likely cause of coronal rain. And then
so would that sort of look like a flickering? Would you expect? I think if probably just a movie of the over the time period might answer that question, because usually in these hotter channels, sometimes the rain typically presents as a decrease, as a sudden decrease in brightness, because you get extinction of UV coming from underneath the loop. So suddenly the loops might go from bright to darker than the back, to sort of decreasing the sides. But anyway, I'll stop.
Well, no, it's a good idea. I would say this. In thermal equilibrium, there's this sort of standard evolution, and the evolution is fairly slow, and then you reach a point where it really accelerates. That's the final thermal collapse that gives you the condensation. But during the slower phase leading up to that, you still can have sizable changes in temperature, which, according to our modeling, should appear in the AAA channels.
Okay. So then there is a question from Milana. Apologies if I missed this, but are you using visual inspection alone to categorize the AlphaH fits? If so, have you considered applying machine learning models or some other algorithmic statistical approach for this task?
Yeah, it's interesting you mentioned that. This was so this method only uses the visual confirmation, or this work, I should say, only uses the visual inspection for the AlphaH fits. We did have a student here who was working on a machine learning approach to picking out the best fit of the data, but that hasn't quite yielded great results yet. But it's something we did think about, yeah.
All right, thank you.
Yeah.
So if you guys have more questions, feel free to ask them.
Yeah, I had one last question regarding remember when you were scaling the intensities from we're trying to look at how the distributions go from. I was wondering if you could explain that just a little bit one more time. I wasn't. Oh yeah, there it is.
Yes.
I didn't say the. So you're scaling by the ratio of the temperatures, of the peak temperatures between the two wavelength passbands.
Yeah, I can send you if you're. Oh, sorry. I can send you this section of my dissertation. It's in prep right now, but I can send you that section if you're interested.
Thank you. Yeah, that would probably be the easiest. Thanks.
Yeah. Can you send me your email? I don't think I have it.
Sure. I'll write it in the chat box.
Awesome.
Okay. More questions? Well, I myself have two questions, and one is a super short one, and the second one is, well, I don't know. So the super short one is actually regarding the slide that you just have right now open. So when you do this temperature scaling, you're essentially assuming an isothermal loop, right?
Yes.
Mm-hmm. Okay, and so one more question regarding the correlation / anti-correlation analysis. So you look at two correlations. So you look at the correlation of diameter and intensity in one viewing angle, and you also look at the correlation of the diameter and diameter in two different viewing angles.
Yes.
And so for a given loop, we have four options. So intensity correlated or not correlated with diameter, and intensity correlated and not correlated with the intensity. For the situation when both diameters, so in the situation diameter anti-correlated and diameter intensity are anti-correlated, that is probably the evidence of the elliptical cross-section. Like, so the loop gets dimmer as it gets wider, and the loop gets wider in one view as it gets narrower in the other view. So in the situation when that both correlations are positive, so the loop gets wider in both viewing angles, and the loop gets brighter as it gets wider.
Yeah.
So that would be the evidence, I would imagine, of something that is full of plasma of the same. And so it's a circular cross section, and the intensity not changing. So the line of sight integration is making stuff look brighter if the intensity is not changing. Can you speculate about the other two options? I mean, I'm feeling a mental 2x2 table.
Yeah. So that would be. Hold on. So we have correlated, anti. Okay. So we have the anti-correlated accounted for. We have, I think, positive accounted for. So one would be positive diameter. No, maybe this is the one you just said. Positive diameter correlation and anti-correlated diameter intensity correlation. That's one of the one you just mentioned?
So positive in both. So positive in both means that it gets wider and it gets brighter in all channels. Yes. And that would make sense if the intensity doesn't change and the diameter is circular, right?
Mm-hmm.
Now, if the diameter changes, if the diameter increases in both viewing angles and the intensity drops as it increases, then I guess we just have the gravitationally stratified atmosphere, right?
I think so. Or
right, you're getting emissivity, right, as distinct from intensity.
Yeah.
Good point.
So you're exactly right. If the diameters are correlated in the two views, and both show, let's say, an anti-correlation between diameter and intensity, that's just showing that the emissivity is changing. For example, because of stratification, gravitational stratification.
Okay, and then the last option. I wonder if it was common, and if it was common enough, then maybe we need to think about some explanations for that.
Yeah, I can. So that's where diameter is anti-correlated, and then we have correlated intensity and diameter. Maybe.
Mm-hmm.
I was just gonna ask, it might be possible. Would it be possible to model how extreme does the aspect ratio of a loop need to be before, once it's seen in this edge-on perspective, it becomes no longer detectable. So you could try to simulate. You could try to see if this explanation for why the loops are missing is necessarily feasible, because even though the loop plasma is now along a line, you still have all of it. So it should still appear. You should simply just see like a narrower loop, but so that may not necessarily be the explanation for why the loops are missing. I'm not sure if the resolution of the instrument plays a role, because stereo and STO have different resolution, different sensitivities as well. Are the loops that are not being seen, are they actually the dimmer loops, which then potentially stereo would not even see them? Maybe they just couldn't. Maybe the instrument couldn't detect them because they were too dim. Sorry, these are just some ideas that came into my mind.
Well, I would say that Terry Kuchera has started to look at exactly that. Let's say you see a loop that seems to not expand, but you can assume that it really is expanding along line of sight. So you know how much plasma is there because you observe it. So assume it expands along the line of sight, and then take that loop and rotate it 90 degrees. So now you're looking at it sort of along the fat dimension, and plunk that down on your image and see if you can detect it in your image, because it will be fainter. But the loop in this case should be fainter, but it should be expanding with height in the new view, the imagined view, and you can ask whether or not you can detect it given a realistic solar background. I didn't explain it very well. Actually, Terry's trying to do essentially what you're suggesting.
Oh, nice. Right, and then from what you said, it seems like actually the narrow edge should be brighter because you've concentrated all your loop into one line of sight versus the flatter end, which will be more translucent. Okay.
Right.
Yeah,
exactly that.
It appears shorter because the upper levels are fading out relative to the background.
Terry, you're here. Great. Sorry, I should have let you talk about this.
Yeah. Well, I mean, we are running out of time, so I have to thank the speaker and the audience again, and and thank you very much, Marika.
Yeah, thank you for having me, and thank you for the great conversation.
Thank you.